Alrighty then. So the sulfonation. Guess what this is going to do? Sulfonate. No. Right. Okay. And so what we're going to have here is we're going to have concentrated hydrosulfuric acid, excuse me. Apparently I didn't have enough water and coffee this morning. Okay. And again, remember that this is going to be one of those substitutions. Energetically, it's extremely unfavorable to break the aromaticity, right? So one of the things that you're going to notice in these patterns is reestablishing aromaticity is always a very important part of these reactions, right? Okay, and so if I ever draw a product out, by the way, and I'm doing a reaction, and I break the aromaticity and I never get it reestablished by the end, what do I know about what I just did? Bad. Yeah, bad. Yeah, it's not quite right, is it? And whatever step that I failed to do that, I need to go back and go, I need to reestablish that somehow, don't I? Okay. And so notice what this is right here. If it's a double-sided arrow like that, then it is a reversible or equilibrium, right? And so this reaction will actually go back and forth like this, indeed. So if you have water with this bensulfonic acid right here, this will go back to benzene and sulfonate, right? Hydrosulfuric acid, actually. Okay, this is actually the mechanism of this reaction. And so what you'll see, it's very, very analogous to the nitration reaction, isn't it? And it's actually very analogous to all the other electrophilic aromatic substitutions, right? So for what's the first step of all these reactions? We establish our reactive intermediate, right? Something very reactive that's so high energy that it can actually make that energetic jump to breaking our aromaticity for temporarily, right? And then so the first thing we're going to do is we're going to protonate one of these OH groups on sulfuric acid. That's then going to leave as our H2O plus good leaving group. That actually is going to cause this bond here to get sucked into this sulfur. You'll notice this is actually kind of an interesting behavior that you may be a little counterintuitive to you, right? Sulfur is less electronegative. It's taking electrons from oxygen, isn't it? Anybody know why it can do that? Okay, so think of you're playing tug of war, right? And you outweigh the other person by 50 pounds. Who's winning? You. Yeah, you're winning, right? And then they get two bodybuilders to join them and help them out. Now who's winning? Them, yeah. They're winning now. And that's actually what's happening right here. See the oxygens here? Those are pulling that electron density. They have to pull through sulfur though, right? Okay. And so what you're going to see here is you form that double bond. That's going to be a protonated double bond. This step right here is actually going to be the heterolysis, meaning unevenly breaking a bond. And so what's going to happen here is the sulfur is going to take electrons from this pi bond right here. This is going to allow us to reestablish the electrons on oxygen, so it no longer has a positive charge. Okay. Notice that is our electrophile right there, isn't it? Okay. All right. So the next step, we now have a broken aromatic system with a carbocation right there, and we have that acidic proton that's attached to this carbon here, right? And so we're going to get the electrophile elimination, or another way of saying that is you're losing the proton, right? Proton transfer. So that's our electrophile elimination. That's going to establish our double bond, reestablishing our aromatic system. Everybody okay with that so far? Okay. Fantastic. All right. So the concentration of the SO3H plus electrophile is going to increase if we have fuming sulfuric acid. Whenever you see those words fuming, what do you think that means? Yeah. So whenever you see those words, they're highly reactive, so reactive they're actually causing a fume of the reactant usually to develop over the solution. Okay? And one of the things you always want to keep in mind if you see fuming and you have heard fuming, if you're using them as a reactant, they're actually quite dangerous, right? Because how well can you control a gas? Not so well, even if it's fairly dense, right? Okay. So be careful if you're ever using something like this. Okay, so this right here is that sulfonation intermediate right there. It is an equilibrium. Okay, so this is actually the desulfonation reaction. This is just the previous reaction flipped, right? Because we had an equilibrium, we're going backwards now. And so what we have is we have the sulfonate here, right there. We have it in the presence of water. We have it with some dilute H2SO4. And what we're going to see is we're actually going to remove this group, and it's going to get replaced with the hydrogen, because it's actually the direct equilibrium going exactly backwards. Okay? It's the reverse reaction in the truest sense. All right. Note, by the way, you do need H plus here, because what did you notice about the mechanism over here? If we go backwards in this mechanism, it would require an H plus attacking, wouldn't it? See that? When removed an H plus in this mechanism, this would have the H plus attacking from here. Okay. All right, so let's talk a bit about Friedel-Crafts and some of the considerations for our carbocation rearrangements and our synthesis of our alkyl benzenes. So whenever we have the Friedel-Crafts acylation, this is going to make a new carbon-carbon bond without risking a carbocation rearrangement. It's the workaround for the problem of the carbocation rearrangement for this Friedel-Crafts alkylation is the acylation instead. Then we follow it with what's called the Clemenson reduction. This being a reduction right here, right? Can you see the metal? The metal is a big hint whenever you see those. Hydride, metal, those are hints that it's a reduction. Okay? So always sort of check those out and look for those. Anybody know the difference between alkylation and acylation? No? Anybody do any biochem sort of stuff? Or cell biology or any of those courses? Biology? Okay. Okay. So, what's the end of a fatty acid? Anybody know? Yeah, so it's actually an acyl. Yeah. So that's an acyl linkage. Okay? And it's usually linked together with something else. Sphingosine, phosphates, glycerin. And that right there is an acyl linkage. So acylation is where you have the carbon chain with a carbonyl on it. Everybody see it okay? Alkylation, on the other hand, would not have the carbonyl, right? No carbonyl there. Okay. All right, so this is the acylation right here. And notice that when we do this reaction here, where we do the acylation instead, what do you notice about this ring? How many groups did we substitute on there? Only one, right? We didn't get 2, 3, none of that stuff, right? No mixture. Okay? Alkylation would have given us a mixture, wouldn't it? So what is happening here is this is actually making this into a worse reactive product. So this product right here is actually not as reactive as this one is for this reaction. Anybody have any idea why that would be? So the benzenes are stable. So what is the first thing we have to make on these reactions? We have to make a carbocation, right? So when we alkylate it, it adds more electron density that goes onto this ring and stabilizes carbocations, doesn't it? Makes it more reactive when we add more alkyl groups to it. Okay. Right here, that carbon right there, that's not negative, is it? That's positive, right? So if you put something positive next to something positive, is that going to stabilize it? No. Yeah, we're going to actually be pushing against that, aren't we? Yeah, so this actually makes it less reactive. Okay? Remember those EWGs that you kept seeing in my previous work? Electron withdrawing group. Okay? EDG, electron donating group. Okay? This is a electron withdrawing group, isn't it? All right, and so the next part of here is actually just a typical reduction that you've seen numerous times. This is just very specific conditions for it, where we're reducing across this carbonyl, and we're reducing it all the way down to cut off the carbonyl and get hydrogens in that location, right? Okay. And so that's the next step. Let's go ahead and try it out a bit. So show how you would synthesize this compound using benzene as the only aromatic starting compound. How would you get that? Who thinks this is going to involve Friedel-Crafts acylation? That's fair. Yeah. Typically, they involve one of the things I just talked about, right? Okay. Yep. Give a good attempt, solid attempt, and then we'll go ahead and move on. So is an alkylation here going to work well? No. It's going to be problematic, right? It's problematic for a few reasons, but there's one really big one, right? Why an alkylation won't work. And that's that we generate a primary carbocation, right? If we generate a primary carbocation, what's going to happen to this carbocation? Will it stay there? No. This is going to rearrange, won't it? To a secondary position. Actually, it'll probably rearrange all the way to the tertiary. We'll just keep getting hydride shifts, right? So, we're not going to be able to get that to work, are we? That would have been really elegant, right? But, alas. The limits of reality. Okay, so the Friedel-Crafts acylation is going to probably work much better, okay? Because it's going to target our carbonyl location, right? That actually helps to stabilize it whenever we make our carbocation here. And so the first step in the retrosynthesis is going to be undoing that carbonyl reduction, because we don't have a carbonyl in the final product, right? And then the second steps is going to be undoing that Friedel-Crafts acylation, which is this step right here. And that would be where we would join it right there. Okay, everybody good with that so far? Okay. Now if we flip this around and we put our reaction conditions, this is what the synthesis looks like. So we have a benzene ring. We then have this acyl chloride. And then what we do is we put aluminum chloride here. That's going to be generating our carbocation to do the attack. That's going to cause our EAS. It's going to keep our carbocation from rearranging because of that wonderful carbonyl right there. Okay. And then the next step is going to be the reduction, right? We don't want a carbonyl on the end, do we? Okay. And so we're going to have to put it with our reduction right there. And that's the HCl and zinc mercury. Mm-hmm.
So for the carbonyl reduction, we just have to draw on OH groups for that, or for the carbonyl reduction in the synthesis to show where the double bonded O is coming from. We have to draw on
No, no, you just have the carbonyl here.
Okay.
And then you put the reaction conditions here. I'm not sure if I understand the question you're asking.
Never mind.
Okay. Did it make sense or
Kind of.
kind of? Okay. 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 Like you wouldn't have to go through the steps of the reaction because we just want to do a synthetic pathway.
Okay.
Yeah. So this would all go in one reaction step, one adding things to your flask. Is that making better sense? Okay. Okay. All right. So here we have the organic synthesis, some common reactions used along with our electrophilic aromatic substitution reactions. You've been seeing that basically we have this little core we're working around right now, and then we're sort of joining up the other reactions we've talked about, or at least mechanisms we've talked about, into this so you can have a joined set of tools to work around, right? And so the next part here is we can get, for example, benzoic acid from benzene. This can require a multi-step synthesis because we can't just add the formic acid group here. It wouldn't be possible. So the first part of this is to put a target on that can be reactive, right? And so one of the ways to do this would be putting a pretty good elimination group on. For example, bromide, right? Okay, and so we go ahead and do a reaction that we've learned at the beginning of the chapter, which is the Br2 with FeBr3. Everybody good with that one so far? And you can think of that as like putting our dominoes, you know how you do dominoes, they stack them up, and you get them ready so that you can knock them over and they knock other things over. Or another way of thinking of this is we're putting our target, we're marking our position, we're increasing that energy so that we have a target that has a good leaving group and we can do this reaction to, right? Okay, so the next step here is we're actually going to be doing the dissolving metal reduction. This is actually a Grignard reagent, right? So we're setting up a Grignard reagent to improve the ability of this target to be reacted with, right? So that we can react this target even better. So we're setting it up higher energy, kind of like your dominoes where you do all those little arcs so you can go down it and gain energy, right? Okay. Does anybody even look at or do dominoes? Ever? When they're a kid? No? Okay. Cool. So this would be setting up my target so I can knock it down better, right? All right. And then I put my magnesium in here. This right here is telling me Grignards because I'm putting magnesium metal in so that I can reduce this and give this electron density. Okay. All right, so the next step here is going to be targeting my now very energetically favorable to react position. And so I'm going to put CO2 gas along with HCl and H2O. Notice the CO2 is to put that carbon and oxygens on, and then the HCl is actually to acidify this. Otherwise, I would have the conjugate base of it, right? The O minus with the double bond oxygen, like the acetate versus acetic acid. Just it's formic acid right now. Or benzoic acid, actually, once we have the benzene. Okay. Now, once I have benzoic acid, I can actually get this from a variety of different ways. So it's not only one method that we could use to do any of these. Okay? So, for example, I could put this under very powerful oxidizing conditions, and then I'd get that oxides on there. And then I could acidify those oxides to put the hydrogen on and get the acid form. So one of the better ways to do this would be, for example, I could acylate it and get an acylbenzene. And then I could react it under very powerful oxidizing conditions, which is that potassium permanganate with KOH and heat. That would fully oxidize this group right here. And that would give me my benzoic acid. Okay. I could have a triple bond. I could have a double bond. Remember those reactions where we cleave the triple and double bonds? And last semester, we put it with potassium permanganate. And the only way we could keep it from doing that is we would do very dilute under cold conditions, right? Okay. And so these are another way I could get my benzoic acid. Now, what if this position right here was quaternary? Can I do this oxidation reaction then? No. Yeah, what this depends on is it depends on a base stripping a hydrogen from it, right? If I don't have a hydrogen to strip, then that's not going to give me my product, is it? No. And so, if I have the quaternary one, I can't go past that. Right. So let's propose a synthesis for the ethyl benzoate from the benzene and any other compounds containing 2 or fewer carbon atoms. What sort of group is this, by the way? Ester, right? Ester. So that's an ester. Okay. So if you remember back and think back to last semester, we had a whole series of esterification reactions. This is going to involve some of those, right? Okay. So right now we're just joining together previous reactions we've learned with our new EAS techniques, right? So we can get aromatic groups substituted and put into these reactions. Okay. All right, let's go ahead and work on a bit. One of the ways that we would want to do this is benzoic acid. This was one of the what we called carboxylic acid derivatives, right? We had a whole series of reactions where we take different carboxylic acid derivatives and get them from one to the next. Going back and forth, right? Whole chapter. Okay. And so this is a really good place to start because we just did a nice little benzoic acid portion, right? Variety of methods to get benzoic acid. And so the first thing we're going to do is undo esterification for our retrosynthesis because we want to get to a benzoic acid as part of this reaction. And this was going to give us that series of reactions. So this is the undo esterification. In this case right here, we actually have an alcohol. There's actually a whole variety of these that we could have done. The alcohol one's just the simplest. All right, so the next step would be that we have a few different ways we can do this again. Remember, I've given you, about 5 different ways of doing each of these reactions because I gave you a branching table each time. So there's 5 times 5? Different pathways you could take here. But the one I would recommend is here an oxidation of the acyl substitution because that's the one I spent the most time on, right? So that's hopefully freshest in your mind. Okay, so this is going to be the undo oxidation, where we oxidize this down to benzoic acid. This right here is the acyl group. So the next thing we're going to do is we're going to do undo acylation for the retrosynthesis. Now what we do with the retrosynthesis, we flip it, and then we add the reaction conditions, right? Remember, this is like sketching out an outline for a rough draft of paper, right? And so we're going to go ahead and do, right here is the acylation reaction. Notice right here we have an acyl chloride, right? Which is one of the nice carboxylic acid derivatives. This is the most reactive one, wasn't it? Okay. And this is going to be with aluminum chloride because we want to attack a benzene ring. So we need to do that Lewis acid setup where we're generating carbocation. And so now we have our acyl group on here. Notice that this is somewhat important because it gives us our carbonyl here, but even more so, it only does it once on this ring, right? We only want it to be done once on that ring. Okay, so the next step right here is going to be oxidizing conditions. So potassium permanganate with KOH and heat. This is going to fully oxidize this carbonyl position. Any positively charged carbon position, this is going to end up fully oxidizing right across. Okay? And this would actually give us the oxygen here with single bond and negative charge, right? Okay, that would be the benzoic, or benzoate, to be specific, which is the conjugate base of benzoic acid, right? We want benzoic acid, so we need to put a little bit of acid in there, don't we? Okay. So we put some HCl in water. That's going to give us the acidified form of that. Okay. So the next step here matches actually really, really well because this requires acid conditions. Notice, by the way, when we put HCl in here, what do we do to this reaction? It requires KOH as part of that reaction, right? What happens if you put an acid and base together? Proton transfer neutralization, right? So we actually neutralized our previous reaction conditions. Okay? So we're going to go on to the next part where we're going to take this alcohol here. This is going to have those extra carbons right there that we want to add. And we're going to do an esterification. This is going to be in the presence of an acid. So this is the acid catalyzed esterification. Okay? And that's going to give us right here the ester. Notice that is actually the same reaction that happens in like biological samples. And for example, is one of the ways you disassemble and reassemble fatty acids across your stomach lining. Okay? Okay. It's actually one of the reasons why your stomach's acidic. Okay. Now, this is going to be the reduction of nitrobenzenes to aromatic amines. So before we were adding nitros to these, right? And you may have been like, that's neat. I've heard of nitroglycerin. Cool. Okay. But what else does that get me? You knew this was going to be a branching pathway, didn't you? Yeah. Remember, they're all tools to be used for other things. We have such a toolkit now that we can go and expand on, right? All right, so what you have right here is, again, the nitro. Everybody comfortable with that right now? That's the reaction we had just done. Okay. Added a nitro to the benzene ring. So there's several different pathways you could take here. You can do the catalytic hydrogenation. Notice that is the same hydrogenation that you did to all the other double bonds, isn't it? And nitro here has nitrogen, oxygen, double bonds, doesn't it? Yeah. And so this is just an outright reduction with hydrogen. And this is going to give you the amine. Now that amine, all the other reactions that you were always able to do with amines, you can do with that amine. The primary amine, you could put alkyl groups on it. You can do all sorts of things. Okay? It's now a new, brand new target that you can do all sorts of things to. All right? This right here is actually the dissolving metal reduction. So you get the metal into a phase where it can actually do this reduction. You add acid and the metal together, iron in this case. And then you take NaOH to finish the reaction off. And this would actually give you right here this, again, amine. Now, what I want to point out here is that this is actually that reduction right here. Why do you need the NaOH to finish this off? Are amines acid or base? Amines are bases, right? They would go to the ammonium ion. And so under the acidic conditions, we would actually get the NH4 or NH3 in this case plus, right? we'd get the positively charged acidified conjugate acid of this. Okay? Okay. Let's talk a little bit about naming and what these are. These are the anilines, if in case we forgot. And so that was the one where we have a benzene ring with an amine on it. That's aniline. And so there's a few different reactions we can undergo for this next part. One of the things that we want to talk about a little bit is the benzene diazonium ion and our Sandmeyer reactions. So this right here is going to be sodium with NO2 on it and HBr. Notice this actually has to be below 5 degrees Celsius. Everybody knows how to get 5 degrees Celsius or below, right? Yeah, it's the typical ice bath where you put too much water in it. Yeah. Okay. The second reaction condition is actually copper bromide, 2 hours, and then we reflux it. So this will give us bromobenzene, 50% yield. This is a way to go back and forth between these two reactions in case you have, for example, aniline, and you need to get a bromo to do another reaction with it later on. Okay? So this right here is going to be your reaction mechanism. So right here we have the NO2 in the presence of HBr. This is going to cause a proton transfer, and this is going to make nitrous acid in solution. By the way, the abbreviation for nitrous acid is HONO, H-O-N-O. So if you ever hear somebody go HONO, that's what it meant, okay? It's the nitrous acid. The next step of this is going to be heterolysis. Notice again we've generated that OH2 plus, right? That's a great leaving group, so this is going to leave. This is going to give us the nitrosonium ion. It's this ion that has a positive charge that's shared between the oxygen and nitrogen. This is very unstable, very reactive, very high energy. Okay? And so what we're going to see is we actually react the nitrogen. It takes the lone pair off the aniline, nitrogen, and that joins two nitrogens together in this ion form. Okay? Does anybody remember what diazo means? Okay. So di, two, right? Azo. So diazo was actually two nitrogens in this form. It's like the peroxide, right? But for nitrogen. Okay? And it typically only gets made in these very reactive intermediates. You can theoretically get it. It can last for a couple days if kept in very, very specific conditions. Not this one, but diazo compounds in general. But they are quite reactive. So the next step here, after you make the diazonium, is you're going to do a proton transfer of this proton here on this positively charged nitrogen. That'll put the lone pair back on the nitrogen there. And this is going to then give you the N-nitrosamine. So nitros, N, and that's the amine, right? Okay. Again, this is a very, very reactive intermediate, actually. Okay? I would not plan on that sticking around the lab for a long time. All right. Okay, so the next part is going to be the diazonation of the aromatic amine here. So last time we left off here where we had just had the H plus of this acid attacking the oxygen here and giving us about water, right? This is the acid. So we're going to start with that, the proton transfer step right there. That's going to have that proton back on this oxygen here. Now notice this is going to create a resonance structure where we'll have the positive charge on the oxygen here and the positive charge on the nitrogen right there. That's going to make that proton there very acidic. Okay. We'll get the proton transfer, taking that proton off onto our water. That's going to, again, give us this H3O plus. This is going to, again, acidify the OH. That's going to give us that H2O plus again, which is a good leaving group, right? And so the H2O plus is going to leave. This is actually going to give us our diazo. And this is specifically the benzene, because it has a benzene ring, right? Diazo and imium. So diazonium ion. And it's the diazonium ion because it has a positive charge. You see that okay? Okay. Okay, and it gave us out water. Now, the cool thing about this ion here is this is obviously quite reactive, right? Yeah. Everybody's comfortable with the fact that this is incredibly reactive. Okay. Did I lose everybody in the reaction pathway so far? All right. A little bit. Okay. Okay, once you've actually achieved this intermediate that's very reactive, you have to make it in situ. You can actually use this as a starting point for a whole series of reactions. Because if we start off with something very energetically high, right, then jumping over any energy barriers becomes very easy, right? Okay. And so this is the different reactions you can do with this. You can do these with the copper plus catalyst, so copper chloride, copper bromide, copper cyanide. Add a bromide, chloride, cyanide onto your benzene ring. You can do this with potassium iodide, so you add an iodide on there. Look at that. You can even fluorinate it. Add a fluorine on it. HBF4 plus heat is going to give you the fluoride substitution. That's not normally something we could do easily, is it? Because fluoride has a very, very high electronegativity and has really, really dense negative charge around it, right? This right here is getting an alcohol on there. That's how you can make a phenol if you want. And so this would be reacting with water and then copper oxide along with copper nitrate. This right here is actually just putting a hydrogen back on there. And so that would just be like phosphoric acid. It's really an acid is the main part of that. It's just the other acids can also cause other reactions. So phosphoric acid is usually your best bet. So the substitutions, again, are going to require the presence of copper catalysts. These ones right here, these are actually known as the Sandmeyer reactions. The rest of these are just different reactions you can do once you have the benzene diazonium ion. Because that puts at such high energy that you can do all sorts of things with it. Because it's a great leaving group. What's special whenever you have an N2 on something? If that leaves, what does it leave as? Yeah, N2 gas, right? Like 70% of the atmosphere? Not very reactive, is it? Super stable. Gas tends to percolate through everything. So quite convenient, right? Could you get any more benign than generating N2 gas? No. So it's actually a very elegant, kind of cool reaction. Okay, so show how to synthesize benzonitrile from benzene. So we're going to be using that pathway we just did, right? But you just have to do the overall reaction portions. Folks. How'd everybody like the 2-page reaction mechanism? You want to hear something that'll make you feel so much better about being in class with me? So the organic professor I took organic chemistry from used to give us 6-page front and back full mechanism exams. So she would give us beginning, end product, filled out, full reaction conditions, everything. And we would regularly have 2-page mechanisms, front and back, same thing, that you'd have to draw out as an exam every week. Yeah, did that every week. That's it's like a tradition for organic chemistry professors that you like start testing really crazy crap and just making your students go, "Oh my god, I'm gonna die," right before you're ready to retire. Yeah. The class average was 30%. Yeah. Me and two other people. Keep in mind, this was a school where we had 300 people in Organic 1. Yeah. It's actually the same size as this school. We were just a medical feeder school. Yeah. And, yeah.
Medical theater?
Feeder.
Oh, okay.
So if you got a 2.5 at school I went to, you had automatic admission into a medical school. Yeah. The school I went to had only an honors program. There was no non-honors. So, yeah. But anyways, should I do that?
No.
No? You'll get so much practice. She had no homework.
Drama can end with you.
Somehow though, no homework makes it worse, because if you mess up your crazy 6-page pathway
Oh, yeah.
things, then you're just kind of fucked.
Yeah, she ended up, now, admittedly, she at least was somewhat reasonable of a person. And she ended up scaling the grades. But it was actually kind of funny because she had to do a nonlinear scale. Because me and two other people had like 70%. And then the rest of the class had 20-30% before the curve. So, like, there was this group of 10% of the class that had grades that were like twice what everybody else's was. And it was just, oh god.
That's how it felt for me. So, if you like Dylan who had 100% in class and they were all 60.
Yeah. I'll tell you what, I did not learn any organic chemistry in that class. Because it's always cramming. Exactly. Yeah, if you have a week test every week,
Yeah.
it's always cramming. Yeah. There was no studying. I used to go into her office hours. She had an office hour the first semester before the class. And for an hour, I would just like ream her. Like seriously, like, no, you're taking too long to answer. Go, go, go. I only have an hour. Because I had to do the whole chapter, right?
Yeah.
Yeah. And there's no time.
Maybe then she would understand the gravity of what she was doing too.
Yeah. For the rest of the next semester, she never had any office hours on the day of the exam.
You changed her schedule.
Yeah. Yeah. Faculty that had been around for 30-something years.
That's crazy.
Okay. Anyways, so here we have our benzoyl nitrile we're trying to get, right? And so what's the reaction going to look like? Remember, you're just doing the overall synthesis, right? So it's going to look like what I just talked about, right? That's probably your easiest bet, is going ahead and doing this sort of reaction right here, where we do the Sandmeyer reaction, right? Okay, and so we're going to go ahead and do retrosynthetic first. We're going to undo the Sandmeyer reaction. Then we're going to undo the diazo. Undo the reduction, that gets us the NH2. And then undo the nitration, which got us our target on the benzene, right? Got us then to the benzene in the first place. Okay, did I just lose anybody on this step? Mm-hmm.
I'm confused on the reduction.
Okay. The reduction we need because we need an amine up in here. So this part of the reaction, the diazo, this is 2 oxidized to do this reaction with. And so we do the reduction so we can get the aniline first. which allows us to enter this reaction pathway right here. Right here. That make any more sense? So like this wouldn't have worked on a dinitro because the nitrogen right here is positively charged.
Oh.
Yeah. So we can't do this reaction on a nitro. That making more sense?
Yeah.
Okay. And I haven't given you any way to just directly add an amine to a benzene ring. Because we've only done the aromatic electrophile, right? Electrophilic aromatic substitutions. We haven't done any nucleophilic aromatic substitutions. Yeah. By the way, there's nucleophilic aromatic substitutions in case you're wondering. But I don't have infinite time in the semester, right? So you'll just have to always wonder about those. No, we can. Okay. Okay. All right. So, any other places I lost anybody in that retrosynthesis so far? Okay. Okay. And so again, we go ahead and trace that out the other direction to get the full synthetic pathway. And so that first step, that's that nitro reaction. Remember that one from like 1/4 of the way through the chapter? Okay. Okay, so we do the nitration first. By the way, those are actually the reaction conditions you're going to do a very similar reaction for. And you have to be very careful with these reaction conditions because it can very quickly get out of control. Okay? Not in a like dangerous way, just you don't get the product you want. All right. This right here then next is going to be the reduction, and this is going to have the dissolving metal method. That's not the only way you could have done this. You could have done hydrogenation, excuse me. But this is one way you can do it. Okay. Theoretically, we probably don't really need to do the NaOH, but that does allow us to actually get an organic solid out if we want to go ahead and purify this. Okay. Anybody know what would happen if you didn't use the base here? You just left this? What's crack?
Good question.
Drugs, methamphetamine.
Not methamphetamine. It's cocaine.
Yeah.
Okay.
Drugs.
Yeah, it's drugs. So why are they called different things?
Because the method they make to prepare it.
Okay, so the difference between these is actually that one is actually a salt and one is an organic compound. Okay? And that's why you can, for example, mix one of them into like water and take it that way and get it really, really sharp. Anyways. The same thing happens for drugs. Has anybody ever seen where it has a dot HCl behind it for the drug? Yeah, so if you ever look at your medicines, just go through your medicine cabinet, you'll oftentimes see dot and then HCl behind the drug's name. And what that is you actually have, depending on the acidity or basicity, anybody remember that lab we did last semester where we took an acid impurity, and depending on the acidity or basicity, it's going to dissolve in different things, right? So if you have the ionic form, it's going to dissolve as a salt, right? And so it'll become more soluble in water. If you have the non-ionic form, it's going to be more soluble in organic solvents, right? And it won't be soluble in water anymore, will it? Okay. This is actually the same sort of thing. So if you left this NaOH off, you'd actually have the ionic form. You'd have the ammonium salt, right? In this case, it would be NH3 up here plus, and then a chloride with it, right? And if you tried to isolate it, you could actually theoretically isolate this as a salt. Okay? This right here, NaOH, is going to give you the neutral compound, which is not going to be a salt, right? It's going to be an organic compound. And so it would come out in things like hexane extractions, that sort of thing. That's actually what's happening on all these like finishing steps, is we're doing those deprotonations to get the neutral things usually, right? because we're organic chemistry, and so we like to use organic solvents. Okay? But if you wanted to have the salt, you could actually just stay with the salt, right? Okay. Okay. So the next step here is actually going to be taking this aniline. We're going to put it under our, remember that these are actually contrived conditions that we have to set up, right? Okay. And so this is going to be that nitrous acid, the HONO. Everybody okay with HONO? Okay. Kind of fun to say. Everybody want to say it? HONO? Yeah, HONO and sulfuric acid, right? Yeah. Okay. Sounds like a clown, doesn't it? And this is going to give our diazo compound. We're then going to use the Sandmeyer reaction right here, which is the copper cyanide. And that's going to put our cyanide on that diazo spot. Remember, the diazo is going to be that really good leaving group that lets us put almost anything we want on there. Okay? Does anybody have any questions about that reaction right there? No? Any questions in general? We're actually done with the chapter. No? Okay. So we'll just call that a day, I guess. Yeah. Okay. Next class period, we're going to go ahead and cover a bit of the next chapter in our series, which we're going back. Keep in mind that won't be on the next exam, though. The next exam is what day again? Monday. So schedule anything that you want to do, like talk to me before that or anything like that. Okay. Hey.